Okay, so last time we saw that galaxies occur in clusters. There are two basic types of clusters. Rich galaxy clusters that have more than 1,000 galaxies, and so-called poor galaxy clusters, like the local group to which Milky Way belongs, that have less than 1,000 galaxies. I mean, the classification or the division is somewhat arbitrary, but you get a picture. In fact, the number of galaxies in the local group is maybe at most 24 or so. Occurring in clusters, the galaxies could interact or collide with each other, and it's quite probable because a typical distance between the galaxies in a cluster is maybe 10, 20 times their diameter. Okay, so it's quite plausible to expect that they will interact with each other. So let us look at some consequences of collisions, interactions. The first one is that a galaxy can strip gas and dust away from another galaxy. They exert the force of gravitational attraction, right? So they're pulling on each other's material, and there could be a transfer of, in particular, gas and dust from one galaxy to another. Here is a photograph of two spiral galaxies. They are close enough to each other so that the force of gravitational attraction can actually pull the material from one galaxy to another. You can see how the gas and dust is being transferred from one galaxy to another. Related to this is a gravitational distortion of galaxies as they pass near each other. Here is the photograph on the right of the famous Whirlpool Galaxy. And what is the set of images on the left represent intermediate results of a computer simulation that is trying to actually see if this shape of the Whirlpool Galaxy could result from two galaxies interacting with each other and deforming each other. Okay? So basically, in this model, what you do, you model each galaxy with a set of rings occupied by stars, and then you allow them to interact, individual stars in two galaxies to interact with each other gravitationally, and then you just apply the Newton's laws of motion and assume, of course, that the gravitational force is governed by his law of gravity, and then you set them on a particular course and let things develop, right? So what you have here is basically a simulation, and these simulations are not difficult to do. Even on a modest computer, Brock has a mentorship program with local high schools where a grade 12 student can do a project with the faculty at Brock, and that's counted as a credit. So a few years back, I had one student from a local school, and I set him on this type of project. I gave him a program that actually does this, and then he had to change the initial conditions, the speeds and the distance of the two galaxies, how they approach each other, and see what kind of shape emerges from that, right? Then again, we'll never know whether indeed this is how Whirlpool Galaxy was formed, because I've done enough simulations in my research to know that if you get the right set of conditions, you can get basically anything you want, okay? But it is possible that a shape like this can result from the interaction of two galaxies. The next consequence is gas compression and bursts of star formation. So this is famous on the left Cartwheel Galaxy. So basically, what probably happened here is that one of these two galaxies on the right made a bullseye hit on another spiral galaxy. So there was a gas compression and the tidal wave that spreads out through this galaxy that got hit, and you can see at the front of this wave all these young hot luminous stars being formed, right? And there are also stars being formed at the center, but gas and dust at the center of galaxy reddens the image. Okay, and it is thought that this bullseye hit occurred some maybe 10, 20,000 years ago. So that's another example. Then we can also have galaxy mergers. Okay, so what we have here is a photograph at probably infrared or radio wavelengths, I'm not sure, of an elliptical galaxy with multiple nuclei. You can see that this elliptical galaxy has several nuclei. Now, something like that could happen if several galaxies, each with its own nucleus, they merge together, forming these large elliptical galaxies, right? And the individual nuclei became part of this galaxy. And finally, we mentioned that Milky Way and other spiral galaxies have spiral arms, and that the galaxy's gas and dust is concentrated in those spiral arms. And there are waves of increased density of interstellar material, that is gas and dust, that slowly revolve around the galaxy. The individual stars move faster. They overtake the rotating spiral arms. So the question is, how do such spiral arms form? And it's increasingly becoming clearer that these spiral arms, their formation is triggered by interaction between the galaxies. Now, if one thinks about it, it is actually, you would expect that galaxies interact or collide more often in the rich galaxy cluster than in the poor one, right? Because in the rich galaxy cluster, you have many galaxies, and the odds of two of them running into each other or passing near each other are much higher. Right? If you go to a mall on a busy day before Christmas, the odds of running into another person are higher than if you do that during the summer when people are on vacation, so on and so forth. And as we saw, such collisions would trigger star formations and would actually cause the galaxy to use up its gas and dust in forming new stars. This conclusion is in agreement with observations that elliptical galaxies, remember elliptical galaxies have no visible gas and dust, and also SA spirals, those with the least amount of gas and dust among the spirals, that they are more common in rich galaxy clusters than in the poor galaxy clusters. Now, the clusters of galaxies form even bigger clusters, so-called superclusters, which are, in a way, clusters of clusters. Okay? Analogy would be, imagine you want to get a bubble bath, right? So think of each bubble as an individual galaxy cluster, right? And you have many of those getting together, forming bigger structures, the clusters of galaxy clusters. And the local group belongs to one such supercluster, which is called the local supercluster. These superclusters form filaments separated by voids. So you see these filaments formed by the superclusters of galaxies with voids in between. These voids are a few 100,000 light years across. These are the biggest structures that we know of in the universe. And one of the big areas of study in astrophysics these days are these large-scale structures in the universe and how they form. It is thought that the distribution of dark matter throughout the universe is not homogeneous, and the dark matter, by its gravity, pulls in the ordinary matter and eventually results in the formation of galaxies, clusters of galaxies, superclusters, so on and so forth.